Yeah, in this video, I'm going to discuss about the topic of organic reagents from the chapter 4, that is structural theory in organic chemistry. Yes, um, there are three types of organic reagents. The first one is free radicals, second one is electrophiles, and the third one is nucleophiles. Now, let's understand what is homolytic and heterolytic fission before going to free radicals. Let's know something about these concepts now. Yeah. Yes, we'll discuss about homolytic fission now before going to free radicals. What is homolytic fission? Yes, let us assume there is a molecule AB here and the two atoms A and B sharing a pair of electrons by means of a covalent bond here. This is a covalent bond sharing a pair of electrons, both these atoms. So if during the cleavage or the fission, if each of the atoms gets a single electron, as we can see here, this electron and this electron, then this type of fission is called as homolytic fission. That means homo-same. That means the cleavage is taking place in a manner in such a way that each of the atoms gets a single electron here. And this is called as an homolytic fission. And after the fission, each of the electrons will go with each of the atoms. The bond is broken exactly in between. This is what is homolytic fission. Yeah, this is what is homolytic fission, where each of the atoms getting a single electron, and this particular species, which is a result of homolytic fission, are called as free radicals. There are two free radicals here which are produced here. Now in heterolytic fission, let's see this heterolytic fission now, as the name suggests, the two of the electrons which are shared by means of covalent bond. After the fission, both of the electrons are shifted to only one atom. So one of the atoms is getting a positive charge here, as you can see here, and the other atom is getting a negative charge. Depending upon the shifting of the electrons, one of them is getting a positive charge and the other one is negative charge. So this is called as cation and this is called as anion here. So this is what is heterolytic fission. Yes. So now coming back to the free radicals, we're discussing about the free radicals. So free radicals are those which contain a single electron or the unpaired electron which are produced by means of homolytic fission. These are the free radicals produced by means of homolytic fission, each of them carrying an unpaired electron. And the free radicals that's produced are very unstable and they immediately react with other species, so very unstable. Yeah. The examples of free radicals, when we come to the examples here, there are two categories here. One are atoms like Cl free radical, H free radical or O free radical, or the neutral species which are carrying an unpaired electron like NO and NO2. There's talking about this NO, that is nitric oxide. When we look at the Lewis dot structure of this, the nitrogen, we know that its configuration, the atomic number of nitrogen is 7. So configuration is 1s2, 2s2, 2p3. So the outermost electronic configuration is 5 electrons. So the total number of valence electrons in nitric oxide is 5. And when we come to the oxygen here, its atomic number is, we know that it is 8. Okay, so electronic configuration is 1s2, 2s2, and 2p4. So outermost electronic configuration is 1, 2, 3, 4, 5, and 6 electrons. So the number of valence electrons are 6 here. So the total number of valence electrons in this is 11 electrons. So 11 electrons here. So we'll count the number of electrons here in nitric oxide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So there's a single electron, which is unpaired electron now here, which is making it a free radical. Now, let's see another example of this, which is nitrogen dioxide, that is NO2. And when we look at the configuration of this again, this is the number of valence electrons in this is, when you see the electronic configurations, and the outermost configuration here is again 5 electrons in this. See here 5 electrons and 6 here in the oxygen. So there are, as there are 2 oxygens here, 6 into 2 is 12, the total number of 17 valence electrons. So when you count the number of electrons in the Lewis dot structure here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Here the unpaired electron is, which is making it a free radical again. So the examples of free radicals are Cl free radical, H free radical, O free radical, or the neutral species like NO and NO2. Yes. Now let's come to the second category of organic reagents. Those are electrophiles here. Yes, second category. Yes, philes means seeking. So philes means seeking. What is philes means seeking? That means means electron seeking agents. So electrophiles, seeking for electrons. It wants more of electrons. It wants electrons. Or why it wants electrons? Because it is deficient of electrons. So because it is deficient of electrons, it wants the electrons. So it's attracted towards the electrons. What does that mean? It means that it's electron deficient and reacts with electron-rich compounds. So reacts with electron-rich compounds. That is what is electrophiles, electron seeking, and represented by E plus or E. E plus, why E plus? Because it's deficient of electrons, which is indicated by the plus sign here. So it easily reacts with negatively charged compounds or negatively charged species, whatever. So it's electron deficient. That is what is electrophiles. Now coming towards the examples of the electrophiles here, we have again 2 types of compounds here, or 2 categories here again. The first one is, when we go, is positively charged ions or cations. So positively charged ions are nothing but cations like H3O plus, hydronium ion, chloronium ion, Br plus, H plus, or R plus. What are these R plus called? Which are nothing but an alkyl groups, which these alkyl groups which are positively charged are called as carbocations or carbonium ions, alkyl carbocations or carbonium ions. And the second category of this is our octet incomplete compounds like BF3, boron trifluoride, aluminium trichloride, FeCl3 or SO3. This is the second class of compounds. So now let's discuss about neutral compounds like BF3. So let's discuss about this BF3 now. So this BF3, which is boron trifluoride, again, when you look at the electronic configuration of boron here, it is atomic number is 5. You can see here, right? Its atomic number is 5 here. So electronic configuration will be 1s2, 2s2, and 2p1. So outermost electronic configuration is 3 here. Okay. And yeah, 3, see 3 here. So number of valence electrons are 3. And when you come to fluorine, where electronic configuration is 1s2, 2s2, and 2p5, atomic number 9, outermost electronic configuration is 1, 2, 3, 4, 5, 6, 7. 7 number of electrons here. So 7. So 3 for boron, valence electrons, plus 7 for fluorine into 3 because there are 3 fluorines here. Total number of valence electrons is 24 here. And when we look at the structure, again, when we look at the Lewis dot structure of this, we can see that see the total number of electrons for fluorine is 8 here, octet satisfied. This also 8, again octet satisfied. This also 8, octet satisfied. But when we see at the electronic configuration of this boron here, see, when we look at the electronic configuration, outermost configuration here, this one, yes, 1, 2, 3, 4, 5, 6. This is octet incomplete. The central atom, which is a boron here, is not octet complete. It has only 6 electrons. So it's short of 2 electrons. That means it is ready to accept the electrons. So it's react with electron-rich compounds in order to satisfy this electron octet rule. So the boron here, the central atom is octet incomplete, so acting as an electrophile here. And when we look at another example like AlCl3 here, which is aluminium trichloride, aluminum chloride, yes. Again, when you look at the electronic configuration of aluminium with atomic number 13, the outermost electronic configuration of this is 3 here. So 3 number of valence electrons is 3 here, and for chlorine it is 17, and the outermost electronic configuration or the valence electrons is 1, 2, 3, 4, 5, 6, and then 7 here. So 7 into 3, again 24 electrons in this. 24. Again aluminium here, see here, short of 2 electrons, which is octet incomplete, which is making it an electrophile. And one more concept we're discussing here, what are Lewis acids? Lewis acids are electron pair acceptors. Electron pair acceptors. So electrophiles are also electron pair acceptors. So all electrophiles are Lewis acids. So this completes the topic of electrophiles here. In my next video, I'm going to discuss about the nucleophiles.